All right. Thanks everyone for being here. Pleasure to have you all here. And I'll be talking about PDE modeling in Mathematica. Basically, when you are working with a team of engineers and researchers. So, so I want you to imagine you are a researcher you are a researcher in a graduate lab or an engineering team, and you are trying to your team is trying to model various systems using computational tools such as Wolfram Mathematica, and so, I understand sometimes you may need to convince your boss or your supervisor to let you use Wolfram Mathematica to work on this project that you are really excited about. So, my talk is going to be about how you can create these models of physical systems, which are invariably going to involve partial differential equations. So, how do you create these models in a very elegant and modular way so that your code is accessible to your team members, to your colleagues. So, if you are around a team of students or engineers and you want to share your code with your graduate lab or your engineering group, how do you create your code? How do you model in a way that's elegant and that's accessible to your team members? I'll be talking about that. My name is Dr. Safi Ahmed, and I'm an assistant professor of mechanical engineering at the National University of Science and Technology in Pakistan. And I also had the opportunity to attend the Wolfram Summer School, where I developed various fluid flow algorithms using Wolfram language. So, this talk is for you if you belong to an engineering or research team that's using Mathematica, or you would like to pursue your team to use Mathematica for your computations. And we also offer various modeling strategies for partial differential equations that can significantly cut the development time of your project and also lower the cost of, let's say, onboarding new team members, because if your code is elegant and modular and more readable and understandable, it's easy when it comes to the cost, not really the monetary cost, but the time cost of onboarding new members into a working simulation. And I will also provide various ready to use notebooks that will help you adapt these techniques in your own simulations. So let's get started. So consider this modeling challenge where you are in an engineering organization or a research team doing computations, and you will note that in whatever model you're working on, not all parts of your model is going to involve the same physics. So, for instance, here you see on the left, I have a fuel filter system from a motorcycle, and you see that there is a free flow region and the various porous regions, and the flow of fuel in each of these regions is governed by a different set of differential equations. And similarly, here you see the heat flow across an automotive radiator, and the flow of heat within the fluid is governed by a different set of differential equations. It's governed by the energy equations, and the flow of heat through the solid through the radiator is governed by a different set of differential equations. Similarly, uh, if you consider human body, you can say interstitial flow in organs such as a human liver. These organs tends to be porous, and the flow of various bodily fluids within these organs is governed by a different set of differential equations than the flow of these fluids within these vessels. So the point here is that if different parts of your systems follow different physical laws, then no single partial differential equation is going to capture it all. So when we are working with partial differential equations in Mathematica, we have this very elegant function called ND-solve. And basically, this is a function that solves differential equations. And what it does really well is, let's say on the left-hand side, you see that I have taken the Laplacian of this region using the ND-solve function, or the sister function ND-solve value. And it's a very nice small snippet of code that does the job for me. And the part where it gets tricky is that if there is more than one PDE. So, for instance, on the right here, I have something that I worked on during the Wolfram Summer School. And what you see here is basically a flow channel. The flow enters from here at the inlet, and then it flows through this free flow region, and it also flows through this porous region. And the flow of water in each of these regions is governed by a different set of differential equations. So in the free flow region, you have the Navier-Stokes partial differential equations, and in the Brinkman region, you have the in the porous region, you have the Brinkman partial differential equations. And you note, if you compare the code with what we had earlier for the simple geometry, the geometry becomes a little bit complicated, and look what happens to the code. So this is the code that we have, and you immediately note that the, you cannot tell where you have the Navier-Stokes equations in there, where you have the Brakeman equation in there, and you have like if statements flying everywhere. So the point here is that if your model gets even a little bit complicated, then things start to get messy really fast. And so, if your model, if there are different PDEs governing different regions of your system, or your model needs more than one PDE, then things tend to get messy really fast. And so, what if you could model smarter and not harder? And so the advice there is to use the PDE components in Mathematica coupled with the region marker. And the idea here basically is that if you have different PDE components within Mathematica, within your code, if you have different PDE components governing the behavior of different regions within your system, then your code starts to look very modular. So, for instance, in my model here, in one region, I have tagged this region using the region marker, and I've basically the region marker indexes the various different regions within your model. So here I have indexed it as one for the free flow region, and two for the porous region. And so I will apply the different PDE components within the different regions, and that will result in a modular PDE structure and consequently a modular approach to coding. So I will say a few things about the PDE components. Basically, Wolfram language has these built-in PDE components like the fluid flow PDE component or the heat transfer PDE component, and these basically encapsulate the left-hand side of the partial differential equations related to that particular domain. So, for instance, the fluid flow PD component will have the left hand side of the Navier-Stokes equations encoded or encapsulated within it. So, you can use these components, and you may find that maybe a PDE component related to your problem may not exist within Wolfram language, but that does not mean that your problem cannot be solved in Wolfram language, and you can always explicitly write your PDEs, or you can also define a custom PDE component that that you can input in your code, that you can use in your code, and that will make your code more modular and more shareable with your team members. So the way it comes together is uh, is just the way I explained. You have the region marker in different regions of your geometry, and you can implement the various different PDE components. So I have so in my geometry for the free flow region, I have the built-in fluid flow PDE component. But for the porous region, I did not have a PDE component. So what I did is that I built my code PDE component, and then I called it Brickman PDE component, and that basically resulted in a very modular approach to coding. So, and this kind of modularity allows for a very elegant model for a very complicated system. So, for instance, in my system, I had the Navier-Stokes equations for the free flow and the Brakeman equations for the porous flow. And what this modularity allows is that it makes your code accessible to the new team members, and it also makes your code scalable to further problems and reusable in basically the existing if you want to extend your existing code or your existing problem, then this kind of approach can be very can make your code reusable. And so, and uh, as we saw in different domains, this kind of modeling strategy can be applied across domains. So, in each of these examples that we saw earlier, we see that different regions obey different physics or different partial differential equations, but the challenge here is the same. How do we model them in a way that's elegant, that is modular, and accessible for the entire team? So, the way it looks like in action, let's look at the actual code that I wrote. So, first, let's look at the approach where you define the partial differential equations explicitly and you do not use the PDE components, but you do use the region marker. So, uh, let's look at how the code looks like. This is basically the same code that I showed you in the previous slide, in an earlier slide, where I wrote the code without the PDE components, and you can see that there's no distinction where my Navier-Stokes equation is, or my where my Brinkman equation is, and uh, I cannot. I cannot make that distinction, and also there's like if statements flying everywhere. So, yeah, note that yes, this model works, this code works, but it's a very short sighted approach to writing your code. So, and the consequence is that you cannot scale your model, you cannot share your model with a colleague really well, and uh, you cannot reuse this code elegantly in a different project. And even to extend the same project, the same PD model within the same project, if you have this kind of approach, then it's going to be a very short sighted approach, and the model is not going to scale well. So the point is that in complex models, explicitly defining the PDEs can be a short sighted strategy. So what do we do here? Well, let's experiment with a few different approaches. And one of the approach that you have is, as I let you know about the fluid flow PDE component, which is built in Mathematica. And here I have used that component in my second approach to modeling, which you can see here on the right. And if I compare it to my previous approach here, which can be seen here on the left, where I explicitly define the partial differential equations, you can immediately see that the code not only becomes shorter, but the code is more elegant. So, for instance, look how elegantly we have defined the dynamic viscosity, the mass density, and we can also see that the code is like the fluid flow PD component. It tells us that somewhere in our code we have the Navier-Stokes equations. So, so just to give you an idea of how the code becomes more elegant and more readable when you implement the PDE components. Now, another good thing to note here is that since now your code is using the built-in components of Mathematica, and the parsing of these components is optimized by the team of experts at Wolfram Research, so the speed and the stability of this kind of a code would rarely be a concern. And so what you note here is that the code is not only shorter, but it's also easier to read. It's ready to scale to new projects, to new team members, and to also existing team members who may not be so familiar with coding or with Mathematica, or or if you have team members who are basically non-specialists, then you can easily share your code with them, and you can also share this kind of code more easily with your supervisors. So, so here you see that in this code I have implemented the fluid flow PD component, but you did note that my model had a few different regions, and they use different Brinkman. they use different differential equations. So here I found an approach where I could use just one PDE component, but my code needs to show that there are different regions and different equations are applied there. So what do I do about that? Well, uh, what I did there is I wrote my own Brigman PDE component for the region for which the PDE component was not already available within the Wolfram language. And so the idea there is that I used the built-in component, the fluid flow PDE component, and then I used my custom built Brinkman PDE component, and that gives me a modular structure which results in a modular code. And the component that I built, I have pasted the screenshot here, but you can also find it in the materials. And basically, I wrote a component uh, related to that encapsulated the Brinkman partial differential equations, and you can find that you can find the documentation for it in the materials uh, along with this presentation. Okay. So now look at what the resulting code looks like when we compare our approach one, where we had explicitly written the partial differential equations. And then we went to approach two, where we just used the fluid flow BD component. And now in the approach three, where we used the fluid flow BD component, which was the built-in component within Wolfram language. And then we also included our Brickman PD component, which we custom wrote. And you note here that, yes, when going from just the fluid flow PD component to this new code, yes, the code uh, became a little bigger, or the code length became a little bigger. But in this code, you see that you have the fluid flow PD component telling you that gives the Navier-Stokes equations involved. You have the Brinkman PD component explicitly written, which shows you that there is also Brinkman PDEs involved, and that basically shows you just by looking at the code how what kind of model we might have here and what level of complexity we might have in our model, and also the dynamic viscosity, the mass density, and the porosity permeability are also very elegantly defined and easily viewable in our code. So these are the results that we obtain from each of the different approaches. And in this final approach, where I have used the fluid flow PD component alongside the Bridgman PD component, you do note that at this interface, you do see some numerical inconsistencies, and they may be likely due to the structural differences between the built-in fluid flow PD component and the PDE component that I custom wrote. However, this solution is stable, it converges well, and it remains insightful for our practical purposes. So, and this kind of approach, while I demonstrated it in a straight channel, but then these examples that we discussed earlier, they remain exciting directions. So if you are working in any of these fields, then you can learn something from this approach. All right. So alongside this presentation, I have provided these codes, and you can download them. And so what I am calling in this sort of a bundle is a tier one bundle, where you can find the Brinkman PD component that I wrote, and also the coupled flow model, which uses the Brinkman PD component along with the fluid flow PD component. And in this sort of documentation, I have stated what issues we had when we were creating this model, and what attempts we did to solve our issues. And finally, we reached a model and a code that is elegant, that's more modular and more accessible to your team. So these two you can find on the with the presentation materials, or you can also go to this link to download these materials. And the tier two here is that you can create your own PD components using using, if you look at these tier one examples that I have provided, the bundle that I have provided, it offers a very clean starting point for you to create such models in your own domains. So for instance, if you are in the heat exchanger space, or if you are in the filtration systems like we saw, or even in the uh, intertissue flow, or if you want to create a tissue scaffold, then you can use these models provided and aid your own understanding of how we can create such kind of models in Wolfram language, and that can be a starting point to create such models in your own domains. And so this kind of model for modeling pattern, it scales really well with your team or your people. So for instance, if you are a researcher working on a simulation and you want to share your code with the non-generalist or with the non-specialist team members who may not know much about the coding, or may not know much about the Mathematica, then this kind of coding approach is very easy to share with your team members. Or if you are in a graduate lab or an engineering group and you want to share this code, it becomes a lot more easier if you have written your code in this kind of a modular way. Now what this means is that uh, if you have a student or a team member uh, who is working on their code using this kind of an approach, if that student graduates, or if that team member leaves your team, uh, the thing is, the model is not going to walk out with them. And so similarly, if you need to onboard a new person into your team or into a working simulation, you can do that not in weeks but in days. So basically, it will take a lot less time for them to understand your code if you have this kind of an approach to modeling your physical systems. And finally, I would say that this way of coding means that you spend less time debugging and more time discovering. And so I would love to hear if you have, if this has sparked something in you. I would love to hear about it. And you can always download these materials from this website. And I thank you for being here. And I'm happy to keep the conversation going in the comments. Thanks a lot. Yeah, so for the favorite features, I've been using these PDE components in my projects, and these are certainly some of the very good features that these have been some of my favorite features. And otherwise, I love computing in Wolfram language, and basically the way the functions are written, they are very intuitive, and so it really helps me to think alongside alongside coding. And so I like just coding in Wolfram language. So the whole approach, the whole philosophy of how the functions are written within a Wolfram language, so that really helped. Any other questions or comments? I would appreciate those. Yeah, so I'm working on various different models, and recently I have been working in robotics. So basically, we have these models related to you have the slip model for the basically the for a hopping robot. So recently, I'm involved with the coding for that. And so I've been just using Wolfram to create different models and PDEs, and I've been doing that for 10 years. Just recently, I have been working on some robotics projects with it. And I'm also working on topology optimization. So uh, so basically, the idea there is to write your code for topology optimization in a way that's more modular and more elegant, so that it's easier to share it with your team members, and also it is easier to onboard the new learners within this field if they use this kind of approach. If they use Wolfram language, then then that way I can then that way they can it's easier for new people within this field of topology optimization to understand these codes. The codes are traditionally written in MATLAB, and sometimes it can create a gap for them to understand. And so I believe that an approach within the Wolfram language is going to help new learners in that field get on board more quickly. All right. Thanks a lot for being here. I appreciate it and enjoy the Wolfram, the remaining of the Wolfram Tech conference. Thank you.